undergraduate student here at Texas A&M. Those are pictures of me. I'm focusing on motors and software systems, and let's just jump right into it because we are a little short on time. So here's a quick overview of this project. So at Texas A&M, I'm working with Dr. Davis on CYPRES, which is a project that allows us to model both the cyber and the physical aspects of the power grid, especially with things like the Ukraine cyber attacks, along with other things. Cyber attacks are increasing as just general attacks on power grids, so it's really important to model both sides of this. CYPRES goes about this by using a few different subsystems. We have these 5 that I'll show and dive a little bit more into in a minute. But each of these have software systems that let us model the hardware and the software that goes into a power grid. Now we have a problem with CYPRES, and that's that all of these are in separate virtual machines on our test bed, and it makes it really a pain to try to start all these systems up. Sometimes it takes as much as 15 minutes per subsystem, taking it up to an hour to even just get the system up and running for us to run a cyber attack. This also makes our test results very difficult to synthesize because, again, all of our logs, all that information is spread out amongst these different virtual machines. So there's got to be a better way, right? That's where I come in. My goal for this is to wrap CYPRES usage in an automated, user-friendly framework. I'm going to utilize Jenkins, which is historically a software development tool to distribute jobs to the CYPRES testbed and pull back information from the testbed. And then I'm building a results web app as well to show the current testbed status to just streamline the whole process of using the system. So a high-level overview of the system. We have vSphere, which is where all of our virtual machines are stored. Then we have the 3 main virtual machines that are used. We have the core network simulator. We have our Power Worlds power simulator and our DNP3 master RTAC machine. And then our data fusion, of course. And again, I'll go more in depth with this. But the main point of this slide is that Jenkins is controlling all of these things, and then the results web app pulls stuff from both Jenkins and the data fusion. So let's talk a little bit more about those automation subsystems because I just flew by those. First is core. This emulates a wide area network between the substation and control center subnet. So the DNP3 packets that our Power World is generating is getting sent through this core network, which makes it a really primed candidate for being attacked. And in fact, we have simulations where attackers, or intruders I guess, can take over certain devices in the core network, such as this subdev2, and implement maybe a man-in-the-middle attack or an ARP cache poisoning attack, allowing them to redirect DNP3 packets, change DNP3 packets, all of that information. We have monitoring to prevent this, but it boils down to Snort, which is an intrusion detection system, and Wireshark, which just lets us to see general network data to see where things are flowing around and if they're off. And of course, all of these need to be started simultaneously as well, adding to the automation concerns. Next, we have our Power World subsystem. We're using test cases, synthetic models of like Texas bus cases to generate our DNP3 data, which is sent over our core network. And then, since this is a GUI only program, there is an API, but I'll go more into why we can't use that. We'll need to, or users would normally have to manually start it, load up a test case, load up our simulation, and then actually start it. Finally, one of the last ones is our RTAC subsystem, which handles both the DNP3 server and the RTAC implementation. We basically aggregate all of our DNP3 data here, where we can build RTACs that trigger alerts and other like logic based off of the DNP3 data flowing through the system. And this is a even more proprietary, even more draconian user interface software, very drag and drop, so automation of this is also very difficult. Just for posterity, I've included our data fusion subsystem as well. I don't interact too much with this, but it does pull data from all of these subsystems and generate some cool plots that get us cool funding. And then finally, we have our attack and defense. So simulated intruders can hijack those devices in core and implement cyber attacks, whereas us as defenders can monitor the network traffic with Snort or see what the breaker status is to detect our intrusions. So all of that is kind of the test bed. Now let's get into the automation. So my automation process uses Jenkins, which is historically a software continuous integration tool that allows you to break complex processes that's distributed against multiple build machines into like one button forms. It also has a really user-friendly user interface, so users don't even have to know what they're doing. They can just hit a button and say, okay, I know core is running, I know RTAC is running. But how does Jenkins actually work? The core of Jenkins is the concept of a Jenkins agent, which is just any computer that has a local script that needs to be executed remotely. So Jenkins agent, in order to turn a computer into one, all it needs to do is be running a script that comes from our Jenkins controller, which is another computer on the network. Then the controller can send information to the agent that says, hey, run that script that exists on your hard drive. The agents will run that script and send back all of the data that it's currently processing and the current status of the program to the Jenkins controller, which allows for orchestration of these sorts of software systems. So Jenkins jobs, as I mentioned, a job is that order to execute a local script remotely. Jobs allow us to send in specific arguments, so if we want to run a script with a man-in-the-middle attack one day and then a script with an ARP cache attack the next day, then we can just fill in that attack type field with ARP cache or man-in-the-middle or something like that. And these are fully editable by users, so it makes it scalable as well as other topologies. Again, all of our jobs are stored in a nice user-friendly database, and we have a current and previous test status slide that shows us just how everything has been going. So now that we know enough about Jenkins, we can talk about what we use for our current testbed, which is the users will select the core, RTAC, and PowerWorld Jenkins jobs, and Jenkins will use its magic to start up core, PowerWorld, and RTAC consecutively, or actually not consecutively, in parallel. And notice that we can run these on Linux or Windows agents in parallel. Jenkins doesn't care. And finally, once all these are done running, we can run that cyber attack from the simulated PC. So, here's a quick demo video that I put in. When I say quick, I do mean quick. Yeah, I'm really fast with the mouse, that's why it's no, I set that up. But anyway, you can see that there is the user interface. We selected the job, and then immediately these pop up, which is very useful. A few other automation methods. We use AutoHotkey. As I was talking about earlier, a lot of these have graphical user interfaces. AutoHotkey lets you use a CSS-style selector syntax to send events to an application. So for example, if you've ever gone to PowerPoint and hit File, Open, that window pops up, right? And you have to type in your file name or select it from something. These controls right here will select that window, paste in the text of whatever file you want to into that file path, and then click the Open button. So stringing commands like this together allows us to automate even the worst graphical user interfaces. And then finally, for Linux scripts, we need something a little bit more in-depth than shell scripts, something that can let us script out like a conversation between computers, and especially for things like SSH login and for modern software startup. So for that, we're using expect scripts, and this is just an example of something that scripts out an interaction that lets you use secure shell to connect to a virtual machine or something similar. So let's talk about results, because we all like those. Our old system took 289 seconds to start for our core job. Now it takes 43 seconds, which is 6 times faster. Same story with PowerWorld. It went from 57 seconds to 12 seconds. And this is very useful because it also has one-click operation. You don't have to remote in and out of the virtual machine. You can do it from anywhere. It can be parallelized, so you can start core, PowerWorld, and RTAC all at the same time. And it can be called from this GUI front end. Finally, for RTAC, this is one of the worst ones that we had. We only got it down from 71 seconds to 61 seconds. It's worth considering, though, that this 71 seconds to start is from someone who knows all the passwords, knows what the process is to start all of this up, whereas average users probably have not had this process memorized. So this time is very, very optimistic, 71 seconds. So the time savings could have been more. Here's time savings in graphical form. It says the same thing that I said on the last slide. That's more for posterity's sake. And then finally, future action. I'm currently working on the real-time dashboard that tells us what's going on. But the end goal of this is a fully automated test battery. So whenever developers will push changes to a Git repo, then Jenkins will immediately run that attack on our new test bed, so that there has to be no worrying about the infrastructure of the test whatsoever. It's purely set up in that way. So thank you for your time.
Thank you.